Okay, now we are starting with a new topic today. It's the link between the continuous time signals and the discrete time signals, which is known as sampling. This is the procedure that we have to follow for processing mostly continuous time signals, and a majority of physical signals are continuous time signals using discrete time systems. And the fundamental discrete time system that we have in our hands is the computer. And nowadays, we are all processing everything using computers. So how are we going to do that? Of course, only after sampling. And the sampling is a process that converts analog signals to, let's say, digital signals. Digital is a little bit different from discrete time. Or let me put it this way, discrete time is not totally digital. Discrete time is discrete only in time. If you further discretize in the levels, that is the quantization, which will help you to represent a signal magnitude in terms of finitely many bits, okay, that would make a quantized signal. And if it is also discrete time, so discrete time and quantized signal altogether means a digital signal. That is a digital signal. But of course, for that, sampling is necessary. Discrete time, discretization is a process. The other one, quantization, is a different topic, and it may be covered in digital signal processing and some further research topics, or in telecommunications. But we're not going to go into the details of those. That is a different thing for the value. Now, what is sampling? We will define the mathematics of sampling, and we will find the relation between the time domain, continuous time signal and discrete time signal, as well as frequency domain, continuous time signal and discrete time signal. So we will take a look at what's happening in the Fourier transform domain too. Okay, that is the critical way of making the analysis of sampling. The sampling will produce a discrete time signal like this, x of n, from a continuous time signal, x of t, by sampling, as the name suggests, x of t at integer multiples of is the sample, and became the to write what is x of n. So the discrete time signal has a completely different axis as opposed to the time domain. The discrete time signal axis is an index axis. It's not a time axis, actually, because you really don't know what is the time when n is equal to 3, for example. When n is equal to 3, what time does it correspond to? It all depends on what capital T you have chosen. For instance, you can sample this sinusoid at these time instances to obtain these discrete time samples, or you can sample this signal and you sample them with a smaller sampling period and obtain these samples. And when you look at the samples coming from this and this, x1 of n, what am I doing? Sorry. X1 of n coming from here and x2 of n coming from here may be equal to one another. So as you see, the time stretching and the sampling stretching may go together to come up with exactly the same discrete time signal. So the discrete time signal here, the time information is lost.
Sesinizi duyamıyoruz hocam.
Okay, can you hear me now? Okay, good. But I am unable to make the screen sharing because the screen sharing. Okay, now I will do it again. Now I'm back. All right. Sorry for the interruption, just the internet, as you see. So let me repeat what I say. I was saying that the time information is lost when you go to the discrete time signal x of n. We don't know what it corresponds to. You have to explicitly tell me the sampling frequency of or the period in case it corresponds to a continuous time signal. We have periods. Net is very slow because when I do something, when I the whiteboard, it doesn't reflect easily. It goes very late. I hope this will be faster. I just replaced the internet. Okay. So I was saying that the sampling frequency, the knowledge of sampling frequency is necessary to accompany a discrete time signal to make it corresponding to a continuous time signal. So what we will do for the sampling, or how we will visualize sampling, will be something like this. We will have a continuous time signal. Let's write it x of t, something like this, for example, on the time axis. And we will multiply it literally with an impulse train, which we will denote as P of t, consisting of impulses. And these impulses are separated by capital T, like this, on the t-axis. So P of t is an impulse train, and it is also in continuous time. So when we multiply these two, sorry, it's not a summation, it's a multiplication. When we multiply them, we come up with some sort of a impulse train, but with varying magnitudes, and the magnitudes are related to the magnitude of x of t. So let me put in dashed format this x of t, and the output, the multiplication, is something like this. It's an impulse here, another impulse here, another impulse here, 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 etc. Like this. So these impulses will be notated by x sub p of t. It's like sampled version of x of t, but it's not discrete time yet. It's just consisting of impulses, and the separations are, again, capital T. Okay, now let's write the formula of xp of t. Xp of t is the multiplication of x of t and the impulse train. What was the impulse train? It is k or let's say n from minus infinity to infinity delta t minus n times capital T. You see, this right-hand side here is the impulse train. So I just multiplied it. And x, so let me write it in a clearer way. This is therefore equal to, or we could also write it like that. It's equal to, if I change the, if I insert x of t into the summation, and from minus infinity to infinity, when you multiply any x of t with an impulse at a certain position, then that impulse value changes and everything else around it will become zero. So I'm not going to put it as x of t, but I'm going to write x of n times capital T, because look at the impulse that is multiplying, t minus n times capital T. This is at n times capital T, or at t is equal to n times capital T. Therefore, I don't write x of t, I write x of n times capital T. This is the expression that will be using some circuitry evaluated in terms of the magnitude of that impulse. And I will generate x of n from here. This is an auxiliary or intermediate signal, x sub p of t. By the way, I can write the Fourier transform of x sub p of t, which is x sub p of j omega, the Fourier transform, is equal to 1 over 2 pi times the convolution of x of t's Fourier transform and p of t's Fourier transform. So I have to convolve x of j omega and p of j omega. I have to convolve them and scale them by 1 over 2 pi. Multiplication versus convolution. Okay, I'm multiplying in time domain, so I'm convolving in the frequency domain. Now, it is necessary to come up with the Fourier transform of p of t, which is p of j omega, because p of t is an impulse train. This one, this is p of t. Therefore, its Fourier transform is something that we have seen before, which is also another impulse train. It was this 2 pi over capital T summation from minus infinity to infinity delta omega minus k times omega s. I'm writing omega s, but it's essentially something like 2 pi over capital T. That is the sampling frequency. Capital T is the sampling period. 2 pi over capital T is the sampling frequency, and I'm notating sampling frequency as omega sub s. So if p of j omega is an impulse train, when I convolve with an impulse train, what do we get? You may remember this from time domain. If you have a time domain signal, let's say a triangular shape, and you are convolving that triangular shape with an impulse train, what were we doing? We were repeating those the triangular shapes at the positions of the impulses, right? That's how we do convolution with an impulse. I can visualize it like this. For instance, let's assume that x of j omega is a triangular shape. Of course, this is only for illustration purposes, all right? Because it's easy to draw such a thing. With 1 being the peak magnitude, and the bandwidth is omega sub m, for instance, from minus omega sub m to omega sub m. Now we will see soon that after this convolution, we essentially need this x of j omega to be band limited, or the x signal to be a band limited signal. It shouldn't be extending towards plus and minus infinity on the frequency axis, because if it is like that, then convolving with lots of impulses will just contaminate one another. This is x of j omega. The other one is p of j omega, and we will convolve these. Of course, these are periodic. It's just repeating itself at omega s 0 minus omega s 2 omega s, etc. It's a periodic impulse train on the frequency axis, and 2 pi over capital T is the magnitude of that, of each of these impulses. So we have to convolve these two signals. And when we convolve them, we are just going to replicate this x of j omega at the positions of the impulses, which will give us x sub p of j omega. Okay, so when I convolve it with the central impulse, it will be the same triangular shape. Probably it will be scaled. Now the peak is not 1 anymore, but it will be equal to 2 pi over capital T times 1, but there is also a 1 over 2 pi scale, as you see here. So 2 pi's will cancel, and I will have 1 over capital T only. Or if the original magnitude of the triangle was A, then the new, after the convolution, the new thing is going to have A over capital T. And then another triangle around omega s, another one around 2 omega s, another one around 3 omega s, etc. It goes on like that. So this is the Fourier transform, the spectrum, after sampling with an impulse train, after multiplying with an impulse train. We haven't converted to the discrete time yet. It's still continuous time, but it's now consisting of discrete looking impulses. And this is on the continuous omega axis. Now, just by looking at this, we can still make some deductions. For example, what would be these points? This is the bandwidth, omega m, and this point here is omega s minus omega m. You can see that, right? Let me focus a little bit like this. So in order for these separate triangles not to merge and occlude one another, to disturb reconstruction, because reconstruction is very much possible here. How do we do that? We do it, I think we may have something like this, a tool like this, by a low-pass filtering like this. And this is a low-pass filter. So if you just crop the central triangle spectrum, then it will certainly pick only the original triangle, and all the others will be gone, and that would correspond to the x of j omega. So the digital to analog conversion, in a way, or discrete time to continuous time conversion is simply through low-pass filtering, an ideal low-pass filter. And the low-pass filters, what is happening? Wow, I'm even unable to erase this. Sorry. Okay, anyway. The cutoff frequency of this low-pass filter is simple. It is omega s over 2. That is the cutoff frequency. The cutoff frequency is omega s over 2, and simply you get the digital to analog conversion using low-pass filtering. But this works as long as these triangles do not cover one another. And when they start covering, some bad things happen. And what does it correspond to, or what does it mean? But first, let's write the condition for this to work. The condition is omega s minus omega m, the right-hand side point, must be greater than omega m. Let's say greater than or equal to, but equal to is not good enough either. I mean, it should really be greater than omega m, which tells us that omega s must be greater than 2 omega m. This condition is telling me that it is also, also has a name. It's the Nyquist condition. It tells us that sampling frequency, which is omega s, must be more than twice of the maximum signal frequency, which is omega m. You see? So the bandwidth must exist. Omega m corresponds to the bandwidth of the signal. It must be a band-limited signal, in other words. And whatever that maximum frequency is, the sampling frequency must be greater than twice of that. That's also known as the Nyquist condition. If Nyquist condition is met, then you can apply this low-pass filter, the red dotted low-pass filter, to convert the signal into continuous time, back into continuous time. Otherwise, if Nyquist condition is not met, then the situation becomes like this. We have still a band-limited, let's say, signal, and the other repetition of that will be here, and the other repetition of that will be here. But I'm drawing only the magnitudes here. So inside this triangle, it's a complex valued entity. There are some real parts and some imaginary parts. So I'm not telling you that the Fourier transform is actually this triangle, all right? It's just anything within this bounding from minus omega m to omega m, okay? Things in between can be considered as the Fourier transform. And some other parts from the right-hand side and from the left-hand side, they start to occlude one another, and they have to be added up. From those additions, it's impossible to resolve what belongs to the left-hand part and what belongs to the right-hand part. There is no way that you can decode this signal. If you try to decode this signal, it will be utterly wrong. The time signal after digital to analog conversion will look nothing like the time signal that you used to have as x of t. So the reconstruction with this kind of sampling is utterly wrong. If your bandwidth is too high, for example, the triangle is too wide, or it may even be not band limited, it's extending to infinity, then you have to apply a band limiting low pass filter before sampling. What is the band limiting low pass filter's bandwidth? The band limiting with cutoff frequency, we can say, with cutoff frequency equals omega s over 2. So cut off your signal from a place which can be considered as omega s over 2. For instance, if your original triangle was like this, and let's say omega s is here, and therefore omega s over 2 is here, first apply a low pass filter from here, like this. This can be considered as a band limiting filter. This is what you apply, and you crop off all these points, and you now have this shape. Okay, after the band limiting filter, and this one has the maximum frequency content of omega s over 2, and omega s is here. So after sampling with this sampling frequency, the new components will look like this. Which is okay, because there's no overlapping. You just have to compromise, you just have to sacrifice some high frequency content of your signal first, because those high frequencies are too much high frequency that can be fit into your sampling period. Your sampling period is not small enough, or your sampling frequency is not high enough to grab those high frequency information. So you have to sacrifice them. You have to crop off those high frequency harmonics or components before sampling. And after that, you do sampling. If you don't do that sampling, or if those things start overlapping, spectrum case, let's draw a case where these triangles are overlapping a little or too much, it doesn't really matter, but there is an overlapping. These portions, the effect that appears in these portions have a terminology in English and in signal processing. It is called aliasing. And many of the Middle Eastern and Turkish or non-native English-speaking people like me, myself, I'm making a lot of pronunciation mistakes. But this one, I know the correct way of pronouncing it. It's called aliasing. In Middle Eastern and in Turkish way, people usually tend to call it aliasing, which is not correct. It's aliasing. Okay? So just side information. In case you may be talking about these things in your presentations and things like that, please do not say aliasing. It is called aliasing. And aliasing or alias is a meaningful English word. It means something. It's not just a technical terminology. We use it as a technical terminology, but you must have seen or watched some in some Hollywood movies or some other films where this alias term is being used. Alias, for instance, in social media means a name which does not really correspond to you. Okay, you use a different name. Okay, you use, for example, an alias called Superman, and it hides your name. So it's used, alias is something that hides the identity. So these, in this case, the right-hand side and the left probably called this phenomenon to be aliasing. By the way, there was a film called Alias. Okay, who was playing in it? I don't really remember. It may be, I don't know. No, I don't remember. You may, since I'm right now teaching, I cannot do that. But some of you guys may search in Internet movie database, IMDb, Alias. So there is a movie in that way. Alias is hiding the identity, and this is called aliasing. So the critical thing in sampling is, therefore, you must avoid aliasing. All right. You can avoid aliasing in various ways. One way is to take the sampling frequency, this one, larger, to make it larger. If it is larger, if the sampling frequency is a higher frequency, then these triangles will be far away from one another, which is good. Which means higher frequency means lower sampling period. So you must densely sample so that you avoid aliasing. That's a way to do it. But sometimes it's not possible because the bandwidth of the digital content that you are communicating will not let you over some total number of bits per second or samples per second baud rate. And in that case, you cannot do that. So the second alternative that you can consult to would be to apply an anti-aliasing or a band limiting filter. So there's an alternative way of band limiting filter. This is also known as an anti-aliasing filter. You avoid aliasing with that kind of a cropping. Okay, now we will proceed with some examples of aliasing phenomenon from a typical content of a single harmonic, which is called a sinusoid. But since we started a little bit late for chatting purposes, we are also running out of time. It may be a good time to give a break for now, and we will meet like at, so what time is now? It's 14:52, so 15:10. Okay, let's meet then. At 3:10, let's meet. Until then, let me give a break. If you have any questions, collect your questions in your minds. You can ask in the beginning of the next course. So now I'm stopping the recording, and we will continue at 3:10.